So normally when we teach gas laws, we take about a week and a half to teach all the laws and their interrelationships. We don't have that much time this year, so what we're going to do is condense it down to about a class or a class and a half of lessons for this. So the first thing is we're going to talk about all the gas laws, and then we're going to show you how to solve gas laws, and then finally in the next lesson we're going to show you how this affects and impacts the ideal gas law. So before we start solving gas law problems, there are a couple of things we have to know about the individual parameters for the gases: pressure, volume, and temperature. First thing we have to understand is that pressure, force per unit area, it can be measured in many different ways. The units that we are mostly considering are atmospheres and kilopascals. You may hear of millimeters of mercury during a weather report, and pounds per square inch is common in industry, industrial gases and things like that. What's the pressure in the line of the gas? What's the pressure in the cylinder? 200 psi, 5 psi, whatever. So, but we're only going to use these two for our class. This is the conversion between the two. So if I ever say 1 atmosphere equivalent in kPa, that would equal that. You have these numbers on the top of your worksheet anytime, so you don't have to worry about memorizing and converting them. Volume. We're always going to use liters in the ideal gas law. Sometimes we can get away with using milliliters in the combined gas law as long as the units stay consistent from one side of the equation to the other, right? In the ideal gas law, you have to use liters. So we wouldn't say liters or milliliters, making sure that the units are consistent from side to side in your equation. Temperature, everything has to be in Kelvin. Here is the conversion factor, or conversion equation from Kelvin to degrees C. Sometimes the problem will be given in degrees C and you have to convert to Kelvin. Standard temperature and pressure, this is a gas's conditions at a standard condition. And when we say standard condition, we mean that the gas is at 1 atmosphere or equivalent, any one of these, pressure and a temperature of 273 degrees K. So you should know all this, and we're going to use that when we move forward. So the combined gas law is a combination of 3 individual gas laws in which one of the parameters of the gas is being held constant. So Boyle's law, which is useful in diving, is pressure and volume with temperature held constant. Volume and temperature with pressure held constant, that's Charles' law. Pressure and temperature with volume held constant, that's Gay-Lussac's law. When we combine them all, we get the combined gas law. When we add moles, we're going to get the ideal gas law. So when we have temperature fixed or constant, there's an inverse relationship between pressure and volume, and that's Boyle's law. And what it basically is saying is that as in pressure increases, the volume of the gas decreases. And as the pressure decreases, the volume of the gas must increase. And you can see that right here, right? Here I have a very high volume but a very low pressure. Here I have a very high pressure but a very low volume. And the reason why this is because if you look at a box of the gas and it has a certain number of particles in it, and then you look at a smaller box of the same gas with the same number of particles in it, if you were to follow a gas particle, it would take a finite amount of time to hit all 4 walls, where here that time is much shorter. Therefore, for the same length of time, you're getting more and more strikes onto the wall here versus here. And more collisions with the wall or more strikes with the wall, the higher the pressure. Charles' law, on the other hand, has pressure being held constant, and therefore there's a direct relationship, not indirect, direct relationship between temperature and volume of a gas. If one parameter increases, so does the other. So you can see that right here. As my temperature is increasing, so is my volume, and it follows this type of trend. And then this is the general equation. Now, why is that? Because as we add more energy to our system with temperature, our particles are going faster, and they go faster and further in a given period of time. So they want to travel farther. When they travel farther, they expand the gas container that they're in. So that's what's happening. As I add more energy to my system with the temperature, my volume keeps increasing, right? The pressure is the same because the pressure is being held constant. The similar thing is happening when we do Gay-Lussac's law. Instead of pressure, actually, instead of volume, that would be pressure. So this would be pressure, and this would be pressure. And it's the same concept. As the pressure increases, so does the temperature. And you can think of a can of soda in a car doing this, right? The volume of the soda can doesn't change, but as the temperature in the can heats up during being in the hot car, eventually the can explodes because the pressure gets too high, right? And we're adding more and more energy to those particles when they're striking the wall of their container, and therefore the pressure is going up. So when you combine Boyle's, Charles, and Gay-Lussac's laws together, you get the combined gas law, because the likelihood of a parameter being held constant is low, right? But let's just show you that it does work, that if I held one parameter constant, I get the correct law to fall out. So we know that Charles' law is volume over temperature when P is held constant. So if P is held constant, we can just cross it out. And why can we cross it out? Because when we go to solve for it, it's going to self-cancel anyway. And therefore, what you're left with is Charles' law. And you could do that with the other laws too. You could cancel one of those parameters. So you could try it and show you, and on your own, and show you that you can do it. So we're going to use this law to solve all of our gas law problems. And then when we add moles later on, we're going to make that the ideal gas law. So here's how I solve all these gas law problems. It's the same basic approach I do every gas law problem. I look at my problem statement and assign my variables. Now here's a little hint. The initial conditions are always assigned the 1 values, P1, V1, T1. The final conditions are always the 2 values, P2, V2, T2. If you do that, you'll never get mixed up. Now, suppose a parameter is held constant. How would you know? Well, the problem would say so. Temperature is held constant, or at a constant temperature. The problem does not mention the variable at all. A gas at a pressure of 3 atmospheres and 280 degrees Kelvin is then pressurized to 30 atmospheres. What is the new temperature? It doesn't mention volume at all, so you're going to assume that volume is held constant. If a variable is held constant, exit out from both sides of the equation and solve the remaining equation. Make sure you convert all your temperatures to Kelvin. Make sure all your conditions are the same unit on both sides of the equation. Don't be putting liters on one side and milliliters on the other side. It doesn't work. Convert one of the units to the other so you have consistent units across your equation. Set it up, isolate the variable you want to do, and then solve for it. Let's see how it works on the next page. Okay, the first thing I'm going to do is I'm going to assign my variables. So P1, V1, T1, P2, V2, and T2. And those are all equals. Now P1, it says the gas pressure changes from this to this. So that's my P1. And this is my P2. The volume changes from 45 to 40. And the initial temperature is 81°C. So I'm going to put that here for right now because I got to change it, and I'm going to do that. And it says, what is the final temperature? So that's what we're trying to find, right? And I know that when I look at my temperature here, I can't leave it at 81°C, so I'm going to add 273 to that, and that's going to be 254 K. Now remember, K equals 273 plus degrees C, right? So we're going to solve for it, and when we solve for it, this is going to be in degrees K. right? And then I write my general equation here. Sorry for the messiness, and then I can now just put the variables where they go. And you can see that these variables go there, and now I can solve for the problem. Okay, so everything's nice and neat here, and you can see where everything goes. So again, all of these values are down here, right? And then all of these values are on this side. And we're just basically substituting. That goes there. So it's just basically where do they go, and then when we do the math, that's what we get. So our final answer is this. And that would be that right there. But it's asking for me in degrees Celsius. So we know that degrees C is equal to K minus 273. And when we do that, we get 131 here minus 273, and that value here is that. So it looks like we've done the correct thing, and the value looks proper, so we're good to go. Here's our second example, and there's a little bit difference to this one, but let's quickly set up our things. So it's P1, V1, T1, P2, V2, and T2. And we're going to say equals, 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 equals. Now we're going to go back and we're going to put in our variables where we need to go. A sample of nitrogen gas is at a constant temperature of 328 K. Ooh, 328 K. And it's constant, so that means both of these are going to be the same because the temperature doesn't change. A pressure of 5.2, so we start out at 5.25 atm, and a volume of 1.36 liters. The pressure is decreased. Okay, so we're going down in pressure. So that means that the volume will go up. Don't know yet, though. We're going to think about it. So that's atm and a question mark. Now we have to put our little equation over here. P1 V1 over T1 equals P2 V2 over T2. Now I like to kind of get a good understanding of where everything's going, so let's do this. This is going to go here, right? And this is going to go here. Now why? We're not going to do anything with the temperatures. We're actually going to cross them out. Why? We can because they're constant, so they're going to cancel each other out anyway. So then we just have to finish assigning our values, and we did that. And so our new equation is just basically going to be this one right here. P1 V1 equals P2 V2. And so we can do that on the next page. Okay, so we said when temperature remains constant that you have Boyle's law. So we have Boyle's law here. And Boyle's law said that as the pressure increases, the volume decreases, and vice versa. So now that we have all these values here and we've calculated it, we can do a quick self-check. Right? Remember, these get crossed out in the end because they're no longer important in the equation. They're going to cancel each other out anyway. You can do the math and show that. So now what we're going to do this is we can do a quick check to see if we got it right. So we're just going to look at a little imaginary arrow here. Now, what happens to the pressure from here to here? Does it increase or decrease? And you would say, hopefully, that it decreases. So if the pressure goes down, the volume must go up from Boyle's law. And does that happen? Well, it starts out at 1.36 and it goes to 1.73. So yes, the volume does increase, so it looks like we did it right. Okay, example 3 has a couple of things in it that I want to show you. So the first thing, again, all we do is just go down the list. P1, V1, T1, P2, V2, T2. Put our equation over here. P1, V1 equals P2, V2 over T1, and then T2. And we're all set. So now we're going to go through and read all this. A container of HCl gas is compressed to a final pressure of 603 kPa. Well, it says final pressure, so we know that that's not the initial, so we're going to say that's P2. Okay? If the gas was originally at STP conditions, STP stands for standard temperature and pressure, and we said that standard temperature and pressure means 1 atmosphere equivalent and 273 K. So we already know the answer to some of this. So this is 273 K. And the equivalent pressure in kPa for STP is 101.3 kPa. Now you can look that up, or it's on your top of your worksheet. Now, does it mention anything about volume? It asked me what the final temperature is in degrees C, so we got to know what that is. Does it anything about volume? No. So we're going to assume it's constant. And when you assume it's constant, what you're going to do on this side is you can just X it out. It's no longer there. Then you can go through and actually put in the variables where they need to go. So the variable here will go here. 273 will go here. 603 will go here, and our temperature that we're looking for goes here. Now we have a good understanding of where we need to solve. Okay, so I showed you in the before that there's a couple of things that are going on here that you have to be aware of. One is this STP thing, which we've done. Right here, STP, you've already figured that out. And then the final temperature is in degrees C. And the other thing is that we kept volume constant. So there's volume constant here and volume constant here. And so we're going to X that out because it's not going to come into the equation. We've done that. And then once we've done all that, we get this final equation, right? Because this is just going to translate down here with the correct values. Remember the correct values, right? This goes here, this goes here, and then this is here, and this is here, right? And then when we do all that, we get this value. But the answer we want is in temperature in degrees C. So remember, we did that, and we said that degrees C is equal to K minus 273. You can manipulate that if you need to. And so at the end of the day, we get this value here. Now, does that make sense? Let's see. For Gay-Lussac's law, it said that as P increases, so does T. All right, so we look at our thing here. Is P increasing? Is the pressure getting bigger? It is. So pressure is increasing. Therefore, my temperature should be increasing. And is it? It's going from 273 to 1352. So it is increasing. And is it increasing by about a factor of 5? Right? Because right here, this may be a factor of 6. I'm sorry. So let's see here. 6 times 273 is about 1,500, 1,600. And that's what I got. So the magnitude and the direction look to be correct. So we have a self-check that we did it right.